Welcome to this lecture series in group theory. We will continue our discussion on cyclic groups, and let us recall a few things that we need for this lecture. So we saw that if G is a cyclic group, then there is a surjective group homomorphism onto G with the domain group being Z, and conversely. Meaning if there is such a surjective group homomorphism, then G is cyclic. So this was a alternate reformulation of the notion of cyclicity. And let us also recall some two age-old facts. So the first one is that the subgroups of Z are precisely these subgroups, and could also be 0, but these are precisely the subgroups of the group Z. And also that there is a group theoretic interpretation of the notion of GCD. If A and B are integers not both 0, then this holds. Okay, so these are the problems. This one we won't be using in this lecture, so I have marked it with dagger, but this is a very important problem. Basically, the first three problems are meant for you to exercise your isomorphism theorem muscle. These are very important statements, and if you followed the discussion on various isomorphism theorems, especially the fourth isomorphism theorem, you will see what's going on, but one should be able to prove them without any prior knowledge of isomorphism theorems. And we will use these two in this lecture. In fact, this is a generalization of the above, but still, I have separately given them. And this last is a very nice number theoretic problem. Nothing to do with group theory, but you can use what we did in the last lecture. So you can use the cyclicity of Z mod PZ star to solve this problem. But you can also do it directly. Okay. So let's get on with it. The purpose of this lecture is to figure out, or at least get some idea about, what are the subgroups of cyclic groups. So first of all, every subgroup of a cyclic group is cyclic. That's interesting. But we have already seen this in the context of Z. Z is kind of the master cyclic group, and every subgroup of Z looks like this. So every subgroup of Z is a cyclic group. And we can use the same reasoning to prove it, but I will go via a slightly different route. I will go via isomorphism theorem route. So before you see the proof, I encourage you to figure out your own proof, and then look at what I'm going to do. So, okay, so start with a cyclic group. And H be a subgroup of G. And we want to show that H is cyclic. So since G is cyclic, there is a surjective group homomorphism from Z on to G. All right. H is a subgroup, so let me draw that, indicate that in this diagram by this hook arrow. This hook arrow is just the inclusion map, meaning X going to X. All right. Of course, this is a group homomorphism because H is a subgroup. And let us pull it back via the map phi. So this is phi inverse H, the preimage of H under phi. Maybe I should put a bracket. All right, and here, of course, since phi is a group homomorphism and H is a subgroup of G, this is a subgroup of that. And let me also draw the inclusion map here. Okay. But there are two possibilities. Either this is the trivial group, in which case, meaning what? Trivial group meaning this is 0. In which case, since this is surjective, this is also surjective. So let me draw a double arrow. So if this were the trivial group, this would be the identity element. I mean, the only thing here would be the identity element, and hence this would be the trivial subgroup of G, and hence cyclic. So in that case, we have nothing to do. So we may assume that this is not the trivial group, and therefore this is isomorphic to, in fact, this is equal to NZ for some non-zero integer. Because every subgroup of Z is going to look like that for some integer. Since we have ruled out or dealt with the case when this could be trivial, we may assume that this integer is non-zero. But here is the point. This is NZ. And here is what we can do. We can consider this map, which takes, what should I use? Maybe Q, let's say, Q going to NQ. And this is obviously an isomorphism. Okay. And now we consider this composite. So this is an isomorphism and this is a surjective group homomorphism. Therefore, this composite is also a surjective group homomorphism. And what we have done is we have created a surjective group homomorphism onto H with domain Z, and therefore H is cyclic. Since we discussed this is an alternate way to describe cyclicity. So this is proof via a diagram. There is nothing to be written here, and that is why I like it. One just follows the arrows. And isomorphism theorems, although here we did not even need to use any isomorphism theorem, but still. Okay. This next one is also a pretty interesting proposition. Suppose we have a cyclic group of size n and is some positive integer. Then we want to show that for every positive integer which divides n, there is a unique subgroup of that size. Note that if you have a positive integer d such that you have a subgroup of that size sitting inside capital G, then this must happen by Lagrange's theorem. So this is not some extra condition or anything. The interesting thing here is the existence and the uniqueness of a subgroup given its size dividing n. So there's a unique subgroup of a given size which divides n, and that's very interesting. So let's prove it. And again, you can prove it using elementary arguments, but I will go via the isomorphism theorem route. One of my main goals in making this lecture series on algebra, linear algebra and group theory, is for you to be comfortable with the use of isomorphism theorems and using commutative diagrams and all. Okay, so let us first prove existence. Okay. So let D be a divisor of n. Okay, and we want to show that there exists a subgroup of size D sitting inside G. Since G is cyclic, there is a surjective group homomorphism onto G. And the kernel of phi is what? The kernel of phi has to be equal to nz. So let me argue that. Oops. Why is that? Because the first isomorphism theorem says that we have this isomorphism, Z mod kernel phi isomorphic to G. G has size n, so this must also have size n. And it follows that this must then be nz. So we deduce that. Okay. Let k equals n by d, and you will see why we are considering this. Basically, the idea is the following. We want to produce... Okay, let me not spoil it. You will see why have I chosen it this way. So k is defined in that way, and let h be the image of kz under phi. So note that, first of all, kernel of phi is contained in kz, and phi inverse h is equal to kz. This one is because of the first star mark problem. So this is happening because of the first star mark problem, where we use that. And why is that? Okay, so let me first explain why is that. Kernel of phi is contained in kz. That's just simply because kernel of phi is nz, and nz is obviously contained in n by dz. So this was obvious. This follows by that and the first star mark problem. Okay. So we will continue with the above diagram. And this is the natural projection homomorphism. Let the composite be called psi, and since both of these are surjective, so is psi. So psi is a surjective group homomorphism. What is the kernel of psi? Kernel of psi is those things which map to identity under psi, which is same as those things which map inside H under phi, right? And the things which map inside H under phi is phi inverse H, which is just kz. So by first isomorphism theorem, we get Z mod kz is isomorphic to G mod H, right? This is kernel psi. So we get that isomorphism because psi is surjective. And now, by this isomorphism, we have in particular that Z mod Kz, the size is equal to the size of G mod H, which implies K equals the size of G divided by the size of H, which implies n by D equals n by cardinality of H, which implies cardinality of H is D. And that's it. So this is why we chose K as that. And you should think about this proof a little bit more than what I've said. All right. We also need to show uniqueness. So let H be a subgroup of size D. Subgroup of G of size D, maybe that's the way to write it. Subgroup of G of size D. Obviously, then D must divide N. So we have this surjective group homomorphism by cyclicity. Let us fix that. So we have such a group homomorphism. What we will show is that the preimage of H under phi is determined just by D. So if we had two different subgroups of G of size D, they would have the same preimage, but then they must also be equal by surjectivity of phi. So what I'm trying to say is that suppose we had H1 and H2, two different subgroups of size D, and somehow suppose we have shown that their preimages under phi are the same, then they must also be the same, because whatever be the preimage, let's say the preimage is P, if preimage of H1 under phi is P, then what is phi of P? Since phi is surjective, phi of P would be H1, but by the same reasoning, phi of P would also be equal to H2, and hence H1 would be equal to H2. So we'll just show that the preimage is determined by D. Okay, so let us also record that D divides N. And now we continue with this diagram. This is the natural projection map. Of course, that would be surjective. And what is the kernel of the composite? Let's say the composite is psi. Kernel psi is nothing but phi inverse H, right? So we have that by first isomorphism theorem. Since psi is also surjective, the first isomorphism theorem says that we have this isomorphism. Therefore, the size of this is equal to that, which is n by D. And this is same as let's say phi inverse H is, whatever, RZ or some integer R, because phi inverse H is a subgroup of Z, it is going to look like RZ for some integer R. So what is this? This is then R. So R equals n by D. So once we know the size of H, we know phi inverse H must be equal to n by dz. And we have proven what we claimed, that the preimage of H under phi is determined by the size of H, and hence H is unique. May look like a mysterious argument, but it is not if you think about it. All right. Let us also prove something we have already seen via straightforward simple argument, but now we will take the route of isomorphism theorems. So we have some group, and X in the group has finite order. We want to prove this equation, that order of X to the K is this ratio. All right, so let phi be this map. Phi of basically 1 going to X, and in general n going to X to the power n. So we have a surjective group homomorphism onto the subgroup generated by X. All right, and we see that the image of the image of kz is the subgroup generated by x to the k. So this is our clue as to what to do next. Okay, so phi k is x to the k implies phi kz is the subgroup generated by x to the k. Right? And now by the second star marked problem, we have phi inverse of x to the k is kz plus kernel phi. This plus appears because we are using the additive notation in z. In the problem, you'll see a multiplication, but that's because the group z is abelian, and we are using the additive notation. So that's what phi inverse x to the k is. And now, thus, we quotient out by x to the k. Of course, this would be surjective, call it psi. And again, kernel psi is phi inverse of that, which is, as we wrote, kz plus kernel phi, which by the first isomorphism theorem again gives us this isomorphism. All right, but okay, so kernel phi is nothing but that. Why? Because if you apply the first isomorphism theorem here, you'll see it factors through z mod kernel phi and gives an isomorphism here. So if you compare the size of this is order of x, and therefore kernel phi must be that particular subgroup of z. That's the only way you can get that size. So kernel phi is equal to that. And therefore we have, what we have is, do we have an extra page? Yeah, we do have an extra page. So thus, this isomorphism, kz plus kernel phi, gives isomorphism from kz, z mod kz plus order of x z to this quotient. But now we use the fact that the divider, so to say, is GCD k comma order of x z, as we recalled in the beginning of the lecture. And now we can just compare sizes. So the size of the left-hand side is GCD k comma order x z. This is the size. GCD k comma order x is the size of the left-hand side. And the size of the right-hand side is, well, let me not skip a step, is that, which is order x divided by order x to the k, which implies order x to the k is order x divided by GCD k comma order x. And this is what we wanted to show. So very nice application of this isomorphism theorem machinery. Okay, and now let us see a number theoretic consequence. Before that, we have this simple group theoretic fact. So G be a cyclic group of order n, then we want to show that it has exactly these many generators. It's a natural question to ask. A cyclic group has at least one generator. One generator of cardinality 1, I mean. How many such elements are there? So if we look at this formula, basically we are asking how many, or I don't know how to say, k in this range are there such that x to the k has order the same as order of x, which is n. So where x is such that g is that. Since g is cyclic, we can find an x such that this happens, and now we are asking how many k's are there such that order of x to the k is same as order of x, which is n, because the size of G is n. And the previous formula says that this happens precisely when GCD. So the above set is basically equal to GCD k comma n equals 1, which is phi of n. So it's a simple consequence of the previous lemma. And now we can use this to prove something purely number theoretic. We want to show that for any positive integer n, this summation is equal to n. And it's not obvious immediately as to why such a thing should happen, but let's give a proof using what we learned in this lecture. So we have two blobs. On the left side, we will list out all the subgroups of what? So on the left side, we will list out all the subgroups of Z mod nz. And on the right side, we will list out all the elements of the group Z mod nz. Okay. As we saw, for each d dividing n, there is a unique subgroup of Z mod nz of size d. So let us denote that particular subgroup by h sub d. Right? So for each d, there is a subgroup and only one subgroup of size d, provided d divides n, otherwise there is no such subgroup. All right. So we will denote that by hd. And what we will do is we'll join some edges between sort of the vertices here and the vertices there and do a double counting argument. So for an element x here, we will join it with a subgroup h, let's say hd. We will join x with a subgroup hd if and only if the subgroup generated by x is equal to hd. So maybe I will denote that geometrically or pictorially in this fashion. I hope you understand what I mean. So I will join x with hd if the subgroup generated by x is hd. So we'll get a bunch of edges coming out of each. Not each, I mean, every guy here emits exactly one edge. And here you have every guy emitting multiple edges. And what we will do is count the total number of edges in two different ways. So let us count it from the right-hand side. We're asking how many edges does a given element emit? It emits only one edge because it is connected to precisely the subgroup that it generates. So the total number of edges appearing in this entire collection is n, because there are n things here and everything emits exactly one edge. From this perspective, from the left-hand side, if we ask a particular subgroup, fix the d dividing n, and ask hd, how many edges do you emit? As we saw just in the previous corollary, this emits precisely phi d number of edges because it is a cyclic group of size d and hence has exactly these many generators. And it is connected to what things? It is connected to precisely its generators. That's what it is connected to. That's how these edges are defined. So the left-hand side shows that the total number of edges is that. And that's it. That's the proof. So this is called a double counting argument. A very nice application. In the problems later, I will hint that this can be proved directly. You don't need any group theory or anything to prove this. That will be an exercise later. And I guess this is all for this lecture. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.